everyone, welcome back to the channel Code with AKJ. Today is day 40 of solving LeetCode 75 challenge, and today we are solving a very interesting tree problem, that is maximum level sum of a binary tree. So before we begin, don't forget to hit that subscribe button and turn on notifications so you never miss our daily coding challenge updates. Also check out the LeetCode 75 playlist for all previous problems and solutions. So let's get started. So the problem statement says, given the root of a binary tree, the level of its root is 1, the level of its children is 2, and so on. Return the smallest level x such that the sum of all the values of nodes at level x is maximal. So you are given the root of a binary tree. Each level of the tree has some nodes, and we define level 1 as the root, level 2 as its children, and so on. And our task is to find the level with the maximum sum of node values and return the smallest such level if multiple levels have the same sum. So let's understand this problem statement with these two examples. So in this given example, we have given root value 1, 7, 0, 7 minus 8. So the level 1, that is the root level, has value 1, so the sum is 1. So level 2 has two nodes, that is 7 and 0, so the sum of the level 2 values would be 7. And the level 3 contains two nodes with values 7 and minus 8, so the sum of level 3 would be 7 plus minus 8, which is equals to minus 1. So we have three sums, 1, 7, minus 1. So we need to return the level with maximum sum. The level which has maximum sum is 7. So the level we need to return here is 2. So coming to the example 2, we have given root value 989, null, and so on and so forth. So here for the example 2, we will return output 2. So these are the constraints. The number of nodes in the tree is in the range 1 to 10 power 4, and the node value would be in the range minus 10 to the power 5 till 10 power 5. While analyzing the problem statement, the intuitive approach we can think of here is to traverse the entire tree and store node values level by level, and after building this level wise data, we'll compute the sum for each and every level, and we'll compare the sum of each and every level, and we'll find out the maximum sum, and the level which has maximum sum will return that particular level. So that would be our approach. So to build this, we'll use BFS via a cube. So let's do the quick dry run on this given example 1. So I have drawn the binary tree here. So level 1 here is the root level. So level 1 contains node value 1. So the sum here would be 1 for the level 1. Coming to the level 2, the sum would be 7 plus 0, which is 7. Coming to the level 3, the sum would be 7 plus minus 8, that is 7 minus 8, which is minus 1. So we have three sums, that is 1, 7 and minus 1. So the maximum sum here is 7, and the level which has this maximum sum is level 2. So for this given binary tree, we'll return level 2. So let's take another example. So let's again grab all the values. So the level 1 contains node value 1, so the sum would be 1. And level 2 contains node values 6 and 5. So sum would be 6 plus 5, that is 11. And finally the level 3 contains values 2 plus 3 plus 5 plus 4. So the sum would be 5 plus 9, that is 14. So we got three sum values, that is 1, 11 and 14, and the maximum out of these three would be 14. So we'll return level 3 as an answer. So for this given binary tree, our answer would be 3. So this would be our approach. So since we need to traverse this entire tree level wise, we'll use a BFS approach, that is using Q. So the time complexity of this approach would be O of n, as we are visiting each and every node once, and the space complexity of this approach would be O of width, that is width of a tree. In worst case, the number of nodes, that is the width of the tree, could be the number of nodes divided by 2. So in worst, the space complexity would be O of n. So let's understand how our BFS approach works with the help of Q. So we'll go each and every line of our Q-based approach and understand how BFS works. So we'll initially take a Q and we'll push the root value inside it. So we'll run a loop until or unless this Q becomes empty. So our first step here would be to grab the first current node that is present at the front of the Q. Here we'll take few variables, that is current sum, which would be 0 initially, and the level variable, which would be initially 1. So after grabbing this Q dot front value, we'll calculate the current sum. So the current sum becomes 1, and we'll push its left child and right child inside our Q. So our queue contains values 7 and 0, and we'll increment our level value. So again we'll take the q dot front value, that is 7. For every level we'll reinitialize our current sum back to 0. So since we have changed the level, we'll increment our level value, that is from 1 to 2, and we'll reset our current sum value from 1 to 0. Meanwhile, while updating this current sum, we'll compare this current sum with max sum, which will be initially 0. So now we'll iterate over level 2 values and we'll calculate the current sum, update our maximum sum by comparing it with current sum. So here first we'll grab the front value, that is 7. Here current sum value again updates from 0 to 7. We'll pop this 7 value and we'll push its left child and right child. Again we'll take the next value, that is 0. We'll add this to our current sum. So current sum remains same, that is 7. And since we have computed the sum of all the values at this particular level, we'll now compare this current sum with our maximum sum. So here current sum is greater than maximum sum, so we'll update our maximum sum from 0 to 7. So now we have completed our computation for level 2, so we'll increment our level variable from 2 to 3, and our queue contains values 7 and minus 8. So since we have moved to the new level, we'll reset our current sum from 7 to 0. And updating the maximum sum variable, will also make sure to update our answer variable, which would store the level value. So since we have updated from 0 to 7, the answer right now contains the level value 2. Current sum value changes from 0 to 7 while computing this q dot front, and again we'll take minus 8 and we'll add it to our current sum. So our current sum will update from 7 to minus 1. Since current sum is less than maximum sum, the maximum sum remains same and our answer remains same, that is level 2. So since the queue is now empty and we don't have any node values, we'll stop our computation, that is we'll stop our while loop, and we'll return our answer variable, which would store the level value which has maximum sum. So for this given binary tree, our answer would be 2. So in this way our BFS approach works. So let's quickly code this approach and let's submit. So here's the code for our approach which we have taken to solve this particular problem, which is almost an optimal approach. So here the base case would be if root is null, we'll return minus 1. So we'll use queue based approach, that is BFS, queue of tree node type. So initially our step would be to push our root node, and we'll take few variables, that is level number 1 and level answer, which would store the answer of our binary tree, and the maximum sum, which would track the maximum sum of each and every level. So here it would be initially int min, which is the least integer value. So we'll run a while loop until or unless the queue becomes empty. We'll grab the size of the queue. We'll take the current level sum, which would be initially 0. This would be resetting to 0 after the computation of each and every level. So until or unless the size becomes empty of that particular level. So we'll grab the current node with the help of q dot front. We'll pop it from the queue. We'll add that current node value into our current level sum, and we'll push its left child and right child inside our queue. So this happens until or unless that particular level nodes has been computed completely. So after finishing this particular level computation, we'll compare our current level sum with our maximum sum. So if it is greater than maximum sum, we'll update our maximum sum with our current level sum, and we'll update our level answer with that particular level number. So after finishing the computation of that particular level, we'll increase our level number variable. So after all this particular process, if our queue becomes empty, we have processed all the number of nodes in this given binary tree, we'll return our level answer, which would store the level which contains maximum sum. So let's run this code. It's working. So let's submit. As you can see, this gives us successful submission. This problem is a classic example where BFS gives an optimal solution naturally. So here the time complexity would be O of n, as we are visiting each and every node once, and the space complexity here would be O of n due to the queue for level order traversal. So to summarize, we have used level order traversal, that is using BFS. We have tracked the sum at each level. We have keep updating the level with the maximum sum. So in this way our BFS approach works, and in this way we have solved this problem statement optimally. So that's it for today. If you enjoyed this breakdown, leave a like, drop a comment with your doubts or feedback, and of course subscribe to the channel for more. Check out the other videos from the playlist to stay consistent and complete the challenge. So until next time, happy coding. Thank you.